Good afternoon, everyone. Welcome to this week's installment of the BMSC Research Seminar Series. It's been ongoing for decades, and the seminar series is a great opportunity to learn from experts in our community about the new discoveries being made in various fields of marine science. And it also supports our vision to create an open, collaborative, and approachable community of scientists at BMSC. So the Banfield Marine Sciences Center, BMSC, is located on the west coast of Vancouver Island within the traditional territories of the Huu-ay-aht First Nation, and we're a not-for-profit registered Canadian charity and shared campus of the University of Alberta, British Columbia, Calgary, Victoria, as well as Simon Fraser University. If you're enjoying this seminar series and want to see more or anything else that we're doing, please visit our website at banfieldmsc.com. So this week's seminar is going to be a little bit different. We're going to do the Q&A at the end, but also if you have questions throughout the seminar, please feel free to type them at any point into the Q&A button down at the bottom of your screen. And our speaker today will be able to get to some of them as she's proceeding through slides. So yeah, go ahead and do that. And if she doesn't get to them then she certainly will at the end of the talk. So our speaker today is a very special guest, Dr. Amanda Bates, coming all the way from the East Coast of Canada, Canada Research Chair at Memorial University. And we're going to be hearing about thermal safety, environmental variability, and biodiversity change. Must be the sunburn that's getting to my brain. Dr. Amanda Bates was actually a BMSC Fall Program alumnus and uses macroecological approaches to understand how the resilience and functioning of natural systems is changing in response to anthropogenic and natural drivers. Her lab works at biological scales from whole organism physiology up to global biomes by linking patterns observed for individuals, communities, and ecosystems with an overarching goal to create sustainable conservation solutions. I'm just going to ask to unmute the microphone here and ask to start video. Amanda, welcome. Thank you for joining us.
Thanks for inviting me. It's lovely to be here. Can you hear me okay?
I can, yes. Yeah, you sound great.
Great. So I'm going to start my screen share here. Get rid of myself. Okay, so can you see my screen and hear me? Is everything okay and I can start?
Everything looks good from my end here, and I'm seeing it looks great on YouTube as well. So go ahead and start, and the Q&A will pop up when you see it. I'll be able to ask you any questions that are coming through on YouTube at the end of the talk.
Great. Okay, so hi everyone, my name's Amanda. I'm a CRC at Memorial University. I spent a large chunk of my life in Banfield, and so I'll tell you a few stories as I go through my talk today and share a little perspective of basically moving around the world, but being a marine ecologist throughout the whole thing. So I first came to Banfield as a high school student, and then in my undergrad for Louis Drewell's algal course. I did my undergrad at Simon Fraser. I came back and did pub education for several years. And then after I had my daughter, my husband and I returned, and he was the diving and safety officer before Siobhan came. And I did my postdoc in Banfield. So I love the place. It feels like home. And it's just great to be back in Canada. And I had planned to come out to Banfield and do some research this summer, which is when I was going to be giving my original seminar. And I'm sorry I'm not there in person, but I promise to come back as soon as I can. So this will have to do for now. So what I'm going to do today is I'm going to take you on a little tour. And I remember finishing teaching in the fall program, and I was driving a skiff across to Wizard, and I looked out to Folgers, and I thought, oh my gosh, why am I leaving this place? Why am I leaving this place? It's just a moment that's kind of burned in my mind. So let's move on. So what we did is we went to New Zealand, and I really wanted to work in Antarctica. And so I ended up going to New Zealand to Scott Base, but I worked at a beautiful little marine lab in New Zealand. And at the time, my husband was doing a PhD at the University of Melbourne. So we were kind of anchored in Australia for many, many years. So we moved on to Warrnambool at Deakin, which has been voted the most livable city in the world. And then we moved down to Hobart in Tasmania, where I was at the Institute for Marine and Ocean Sciences, right on the water. And then from there, I took a faculty position at the National Oceanography Center in Southampton. and recently have moved back to Canada to work at St. John's, also at a marine lab right on the water. And what I realized is, because I was basically born and bred in Banfield, when I came back to St. John's, I absolutely loved the sound of the aquaria water and the smell of kind of like rusty metal and salt water mixing together when I'm doing my work. It just felt great. And these kind of places are linked because they're all Commonwealth countries, but actually this is a bit of a bias in this kind of data of where we've been, because I almost took a job, or I was basically, the two jobs I first was competing was at Okinawa in Japan at an incredible institute there, which is also on an island. So at some point I just have to acknowledge I really love islands. That's really where I like to live, obviously. And even in Southampton, when we lived in England, we moved to the Isle of Wight. So there you go. So that's a little bit about me and what happened after I left Banfield. And it's just lovely to be back in Canada now. So my research is really looking at what factors are driving biodiversity change in our oceans. And we often work to compare kind of oceans to terrestrial systems. And what really strikes me in my career so far is that I think it's almost impossible to be a basic ecologist now without thinking about some of the human drivers and activities which are reshaping biodiversity on our planet. And this is a surface layer that we generated a couple of years back, looking at just on the surface of the Earth, so surface of the ocean and surface of land, climate change, exploitation uses such as agriculture and farming, human population density, pollution, and invasions. And essentially, we are impacting our entire planet from the surface and now increasingly into our deep oceans where we're mining. And so we are challenged as ecologists to be better communicators, to interact with the public in more kind of direct and inclusive ways, because we have these grand challenges that we're addressing. And what we're seeing is a real shift in diversity. There's so much evidence for extinctions that date hundreds of years back that are directly related to human activities. And so we're definitely losing species, but we're also changing biodiversity because of our interactions with kind of communities at the same time as these have already been relatively reshaped by these drivers. And so my lab is called the Physiological Diversity Lab, and I have a great interest in kind of ecophysiology and understanding how temperature tolerances and temperature preferences and kind of environmental thresholds drive species patterns. And so what I'm doing in my lab now is integrating physiology with community ecology, and what we're trying to do is kind of come up with patterns to look at the physiological diversity of systems. And so if you're interested, please check that out. And so part of this interest comes from I did my PhD at hydrothermal vents, where we have super variability. And then, of course, I went to and kind of stretched this, thinking through long time periods, but also across the globe. And I really realized biologists are really ignoring ocean weather. And so I love variability in kind of environmental systems. The world is an extremely variable place, and trying to capture that and show how that's kind of changing biodiversity and how that in turn impacts or interacts with kind of human uses is what's really driving my research now. So this is actually a slide that I made for my very first job interview. I actually interviewed at Memorial University right out of my PhD in 2008. And I'm still kind of using this basic framework because it really is what links a lot of my work together. And even though I work from individuals now up to the community and even kind of biome scale, today I'm just going to focus on the community ecology side of things, so biodiversity change. And so biodiversity change is really a function of exposure. How exposed are you to different drivers of change? And then how sensitive is that kind of biological unit, be it an individual or a species or an entire kind of system, to that stressor. And I'm interested in temperature, so we'll start there. So temperature, when we communicate about temperature in kind of the popular media, we do so in a relatively simple way. So I've just done a little outline of the box in the upper left-hand corner where there's just basically a checkerboard. So if we imagine that the red is summer and the blue is winter, if we think about warming across this entire kind of spatial grid, what we then might see is a warming in the summer and also a warming in the winter. So we just kind of have even warming across the board, across seasons. And I think that's really what we kind of communicate a lot when we're thinking about global warming and change, is this relatively even shift. But of course, we can have these shifts that occur in kind of different areas. So we can have increases in the mean at different times. We can have shifts. We can have summer that's warming and winter that's cooling. So we're getting greater extremes. And we can also have shifts in the variation. And some of this variability in how temperature is actually changing on our planet versus the scale at which we're measuring biodiversity is what's explaining some of the variability and the trends we're seeing. So let's think about this in a simple way. We've got warming. What do we expect with warming? What's the prediction? And so this is a little figure that I did years ago, but I haven't published it. And I often talk about it because it's a nice, simple kind of figure. We've got our subpolar species here in the red and our polar species here in the blue. And we've got a pole, so we're in a relatively cold kind of system. And what we would expect with warming is an influx of kind of subpolar species as they expand into a warming area that's previously been too cold for them to occupy. And so if we think about temperature on the x-axis and performance on the y-axis, what we have is our polar species that are doing quite well at a relatively cool range, and our subpolar species in the red that are, performing better at a relatively higher kind of temperature range. And in panel C, there's basically a crossover. So with warming, what we see is a decline in the performance of our polar species and an increase in the performance of our subpolar species in the same location. So we're getting this trade-off of species that are coming in and species that are leaving. And when we kind of think about this across a whole geographic range of a species now, we've got one edge of the geographic range, which is limited by cold, and another edge of the geographic range, which is limited by warm. And if we think about this influx, so in the example that I kind of gave, this would be the subpolar species that would be moving into a warming polar area. What we have is that historically we'd have absence, and then we get the arrival of one individual, and we might get some bouncing back and forth, and we get some population increase through time and then persistence. So that species is now kind of a permanent fixture in that community, and it's recognized as being there for most of the year. And if we think about this at the other end, on the warm end, what we have is basically a contraction pathway where we have species that are present and then performance declines as temperature increases, and then the population essentially decreases. So we get a population decline leading to a local extirpation or extinction event. And so basically we're getting the retraction and at one end and the expansion at the other. And so a really key question is, how is this manifesting at a community level where we've got this kind of in and out of species, changes in abundance through time? And this is complicated because, of course, temperature is not evenly warming across all seasons. So these are relatively old papers, but there's some lovely examples of sockeye salmon from our coast, the West Coast, where we have phenological shifts in spawning, for instance. We have distribution shifts where we have that kind of poleward shift that I just went through, but also we have abundance change. And what's interesting is that these abundance changes, these kind of intermediate stages, are really, really strong when you look in long-term data. So if we look at function and how species are actually functioning in communities, the abundance change is a really key kind of metric of functioning because those abundant species are having such a large impact per capita. So basically what we would expect then is shifts in richness, shifts in abundance, and then turnover in species potentially in the community that's related to this kind of community shifts through time. So what I'd like to do now is just highlight a result from a paper that came out this year. And basically this work relied on biotime. This is a database where essentially the premise of the database is that one location has been monitored through time. So in that location, researchers have gone out and they've collected data at one time point. And here what I'm showing is time point 1, and the monitoring sites are kind of in red. And then I've kind of blacked out other areas in this grid, because those might be areas that are urban, or those might be aquaculture sites. Typically, we're not putting our long-term monitoring sites in areas that are likely to have kind of land use or seascape changes. So we're putting them in areas like parks or areas that are protected that we might think are going to have kind of a long duration through time. And then here we have our second time point. And what I've done with the black is just showing that we have a land use or a seascape change in that kind of period, but where we're monitoring has remained green, which is kind of symbolizing that that area is still intact. And so biotime essentially is capturing all of the species that are in a particular area, as well as all of the individual and the counts that are there. And so what we were able to do with this data set is look at how these different assemblages across marine and terrestrial species were responding to temperature change directly. And so each of these little dots in this figure is one location. And at that one location in both marine and terrestrial locations, we have the slope of temperature change. So how was temperature changing in that environment? And then and then on this particular axis, it's across kind of latitude. And what you can see is that there's a huge amount of variability in warming and cooling in both marine and terrestrial systems. So even though there's a net global warming signal, locally, there's quite a lot of variability. And when you take this and kind of match it up with how the community itself is changing, we also see a lot of variability, which is not really that surprising when you kind of think about this in terms of a community context, and then also how variable the world is around these kind of communities and all the different factors that can be driving change. And so what we have in the top panel, for instance, is richness, where the green is the terrestrial and the blue is the marine environment. And the signal is very, very close to zero. So we have a net zero response with a positive or a significant kind of effect of richness in the ocean in this case. So we've seen a little bit of increase in our ocean systems in terms of richness through time. But I just want to emphasize how variable this is. And there's very little explanatory power here. We've got lots of variability around this trend. And so I think that's the major point I want to make with this particular slide, is that biodiversity change is extremely variable. And when we look across these kind of traditional metrics that are based on species identity or abundance, we often are not detecting a signal. It's not as easy to detect a signal if we're using some more direct measures, which I'm going to talk about a little bit later. And so before I kind of shift gears, I wanted to talk for the first time. So we have a paper that's just about to be submitted. And because I'm talking to a group at Banfield, and it's one of my favorite places, and the work actually occurred or was facilitated through the Marine Station, what I wanted to do is talk a little bit about this study. And this study also highlights why we might see lack of change even in an area that's been warming or experienced some extreme temperature events. And so what I'd like to do is take you guys to a chunk of rock that's off the West Coast Trail. It's between Pachina Beach and the lighthouse. And of course, this is tide pool work. And for those of you that have known me my early career, I started working on Anthopleura. I absolutely love the intertidal on the West Coast. It's stunning. And then I worked with Pisaster acraceus for my postdoc work. And so I love these tide pools. And my neighbor in Newfoundland is Dr. John Green. And Dr. John Green was one of the original people who was around when Banfield was first set up. He was a buddy of Dr. Louis Druel. And Shirley Pacula and Louis helped John start collecting data in tide pools off the West Coast Trail in 1966. and it's been monitored now for more than 50 years. So you can imagine, because I love Banfield so much, and then I'm also really interested in community change, and there's been some really interesting temperature events in this area. Of course, I was ready to jump aboard and start analyzing these data. And so what John worked on, he's an honorary research professor now, is he worked on tide pool sculpins. And the site used to be accessible from about, I think it was Bridge 15, but there's been a landslide there since. And it's between, I've outlined it in this white circle here, it's between 1.5 Mile and Cave Beach. And so it's quite difficult to access now, but previously when John started the study and for the first few decades of it, it wasn't as difficult to access. And what John did is he went out, and even with the ecology course, so he used to teach this course, he would go out and put rhodonine in these pools, which is an organic, well, it basically kills all the fish in the pool. And from there, you can ID all the fish and get every single individual that is in the pool. And if anyone's ever looked in a tide pool, you can usually see a few fish. But when John uses this kind of comprehensive sampling technique, you get everything that's in the pool, and there's hundreds of species, or hundreds of individuals, and up to 10 or so species in every single pool. And he did this sampling about 13 times over that 50+ year period. And so, of course, I was dying to see, well, what happened? How did this change? And there was a historical period from 1966 to 1993 where he sampled relatively comprehensively, or like a few times, but then he sampled 5 times between 2012 to 2016. And during that recent event, of course, the temperature blob came in and the area was quite warm. So it's quite interesting to then say, okay, for these tide pool fishes that are relatively physiologically quite robust, they can tolerate really low oxygens, relatively warm temperature. Are we seeing any changes? In addition, these fish aren't commercially harvested. So they're in an area that's now protected. It's a park and wasn't originally when John set up the study, but is now, and they're not commercially harvested. So kind of a cool study system. And so what I've done is I've shown tide pool shore height on the top from low to high up on the shore. And then we're looking at these kind of classic indicators of biodiversity or community, the community structure. Richness, total abundance that was in the pool, the total number of individuals that were found, and then the similarity, in this case using the Bray-Curtis index, how similar were those pools to the first year that they were sampled. And so, cool thing, really the only changes were in the low tide pools. And I'll talk about that a little bit in a sec. But over this whole entire period, even though there was some bouncing around, the communities have stayed relatively persistent and quite resilient to relatively extreme events during this time period. It's pretty fascinating, and it wasn't necessarily what I expected. I thought maybe we'd see some invasions. I thought we'd see some rain shifts. I thought we'd see something. And when we looked in our low pools, there was a bit of a signal. So overall, we were seeing a bit of a change. We were seeing species that were a little bit less abundant in this more recent time period, a little bit of drop in species richness overall, and kind of a decline overall in the community similarity through time. Okay, so now you're an ecological detective. So you have this overall pattern. What's driving it? And honestly, what's driving it was the rare species. So what's kind of interesting here is because John uses this comprehensive sampling technique, he actually gets all of the really rare species in the community. Whereas normally when you're sampling, you miss those rare species. So essentially what happened in this historical time period is there was 8 species that were present, but in this recent period, which was relatively warm, none of them were actually there. And most of these species they have relatively cooler affinities. So they're subtidal species and they're not, not as common in the higher intertidal. So it's likely they just have kind of dropped out of those intertidal pools in this relatively warmer season. The one species that was found that's new, at least here was a species that's more typical of California. Its range goes down to Baja, but British Columbia is kind of its upper range. So that's the one kind of change, and there was only a couple of individuals. So this is really surprising. This is, almost 55 years of data. Cool. Okay, so I think what this kind of shows is that we can have remarkable community stability if the species that are comprising those communities have robust physiologies. We might then expect to see quite a lot of persistence in the face of extreme events or warming or other kind of disturbances. If we have minimal human activities, we can expect kind of a baseline response diversity in the system. And I think what's key here is that in a lot of our community samples, we're missing our rare species. And here in this study anyway, the story was in the rare species. So quality data is really, really fundamental in trying to understand how communities are changing. And oftentimes we're missing a whole component of the community because of those rare species. And I think what this also indicates is that because these species have been quite resilient, there may be quite a rapid tipping point that's reached in the future where these tide pools kind of shift in their composition because some sort of threshold is reached. So I thought that was a lovely example, and it was super fun to talk about for the first time. So now what I'd like to do, and I'm just going to check the time. So now what I'd like to do is shift to a different place in the world and talk a little bit about quality data and a data set that I've been working on and have launched since coming to Canada called Reef Life Survey. And Reef Life Survey is a subtidal monitoring platform. Basically, Graham and Rick started this now over a decade ago. And the idea is to use standardized abundance counts along a 50-meter transect and to use kind of trained scientists who are volunteers, but are also collecting the data. And so we have very, very good skilled divers that are collecting our data. And the idea was to use the same kind of methods throughout the entire world. And there's now thousands and thousands of surveys across the globe, including in Antarctica. And so what I did when I came to Canada, I had some funding and I decided to set up Reef Life Survey Canada. And I had a team of awesome students, as well as Tom Bird, who's on the left for those of you that know Tom, who started Reef Life Survey over a year ago now. And our idea was to start building up these surveys on the East Coast and then hopefully launch some expeditions on the West Coast. And so we've started these surveys here, and why they're really, really useful is because we collect abundance data as well as species counts. And so that abundance data ends up being so key in trying to understand how communities are shifting and changing. And also you can do some interesting kind of things because you have abundance data that you wouldn't otherwise be able to do. And so I'd like to talk a little bit about that now. And so what I've done is I've drawn in gray a whole bunch of populations of a species, let's call it that. And so we have populations of a particular species, and we might imagine that as we move from a warm to a cold part of that species range, that population is going to have a maximum kind of ecological performance that it might achieve with abundance. So its maximum ecological performance could be there, but for the species, if we're looking at that peak might occur, for instance, here, which is where the black line is. And so we wanted to test this. And because we had the Reef Life Survey data, which is collected using the same or relatively similar kind of technique, a large, huge kind of expansive areas, what we were able to do is look at the abundance distribution across the entire geographic range of species. And that's kind of what we see on this left panel here, where the black dots represent where a particular species occurred across the Indo kind of Pacific, and the down on the on both kind of sides of Australia, the west and the east. And then when you match this up to temperature at those particular areas, the black dots are the abundance that particular population in that particular area kind of achieved. And so what we were able to do is show for about 3/4 of species that you do kind of reach this abundance peak. And what we were really interested in is to try and understand if we can use this to then predict how communities are changing. Because now, instead of just having richness or abundance change, we actually have something that is characterizing that species that directly relates to temperature. And so if we're interested in, for instance, how that community is changing with temperature, now we have a response that's directly linked. So what this is essentially the species realized niche. It's a characteristic of that kind of distribution. And what you can do for all species in a community is you can take the peak. And so I've drawn a little, mock community here at Fish, where we've got a range of temperatures for this particular community. And now, instead of having like a Simpson index or something like this, we can now characterize the community as having a particular thermal index. So in this case, the average across all of these would be 19.5 degrees. Okay, so like, who cares? Is this actually useful? And so Paul Day was an honor student who worked on this particular reef. It's Rottnest in Western Australia. It's absolutely beautiful. And a heat wave came into that area in 2011. It was a really strong kind of heat wave. And the question was, can we use these kind of metrics or indices to then predict which species are going to change in that community? And we actually had great predictive capacity using that simple derived indicator that we then could input into a community level. So this realized thermal niche, or these ranges, really can predict which species are going to respond positively to warming and which are going to respond negatively. And then we've looked at this across kind of fish and plankton communities across both the Pacific and the Atlantic Ocean. And in this case, Michael Burrows led the study, and I've shown him, he loves his intertidal system. So I've shown him up here counting some barnacles. And basically what we're interested in here is, does CTI, so this community metric, does it track temperature? And so on our x-axis here, we have change in temperature. On our y-axis, we have change in our community thermal index. And what we would expect is, as temperature increases and change, we'd see a similar increase in the CTI, which would then represent the community changing. And what we found when we did that is, well, in areas that were warming, such as the European kind of system, we mostly had a nice tracking in that system. We also saw the same kind of response, but only in areas that were warming on the Canadian kind of Atlantic side. And then we saw in areas where we weren't getting any change, like in the Pacific, if it was cooling, we saw a decrease, but if there was no change, we didn't see a change in the CTI metric. So what's interesting about this is this metric has now been used in a whole bunch of different places, et cetera, and it's now been kind of indoctrinated as a biodiversity indicator. And so it's called the Reef Fish Thermal Index, and it feeds into the Aichi targets, the Sustainable Development Goals, et cetera. And it's kind of based on this body of work that we did to kind of show as a proof of concept how responsive this index is, and then that it's essentially kind of shifting and responding to temperature. So it's quite useful. So I just saw a question pop up. Don't know if I should take it now. Well, I'll keep rolling because I'm not quite sure where the question button went to. Okay, so we have trends that are up, trends that are down. And when we have really good data quality and we take into consideration ocean variability, both in space and time, and we think about this now as a pseudo experiment where we can formulate predictions of how the community would shift given the species that are present and also given the conditions, we actually see some great predictive capacity of the thermal niche, and ocean communities in particular are extremely sensitive to temperature and are reshuffling and reorganizing quite rapidly. Okay, so what I'm going to do is I have another few minutes and I'd like to take this to the next step. So this is about biodiversity change, but I started my talk by really highlighting the fact that we now can, I guess, move from just thinking about ecology and thinking about how can we conserve, or how can we take our ecological knowledge and then formulate some kind of clever tools or ways of integrating what we're doing into kind of conservation. And so I like to share with you and take you to one of my other kind of favorite places in the world, which is Moriah Island. And Moriah Island is special. It's a park on land. It's an MPA in the water. It's a very well-governed MPA, and it's 7 kilometers of coastline and utterly, utterly stunning. And so this area is also interesting. We're looking at Tasmania, and Moriah Island is a little island off the east coast. And the dark orange and red is the East Australia Current. And this current is increasingly pushing polewards, and with it bringing propagules that are bringing in kind of warm affinity species into this area. And so what we were interested in is, well, what's happening in our marine reserves versus the fish communities during this time. So we have some expectations for how biodiversity is changing, but if we have a protected area, are we seeing any differences? And so this reserve has responded beautifully to protection. This is a blue-throated wrasse. So there's lots of lobsters that have come back in these systems that are, kind of taking on that top predator role. And then larger body fishes have returned, and I'll talk about that in a sec. And the cool thing about this whole design is that Graham Edgar and Neville Barrett had the vision to set up the monitoring in a replicated way before they kind of initiated their monitoring program. So in the MPA, there's 6 replicated sites, and in the fish sites, there are 6 reference areas. So these areas were initially paired to the MPA so that they would be similar in composition and habitat type, and thus allow kind of a direct comparison. So now we have this area where we have protected area, we've got warming, and we can directly compare between the fish, which I've shown in blue, and the MPA, which I've shown in green. We have our CTI metric, which I've argued kind of tracks change through time. And then we have our 2 decades of warming in this area from 92, in this case, 2012. So the first thing to notice is that these communities were both bouncing around a lot. So there's a lot of variability within the community. And this was actually directly related to the El Nino La Nina signal there, where there's lots of runoff and other kind of parameters that are occurring oceanographically. But overall, both communities were warming, but less so for the marine protected area. And one of the clues to that is that in the marine protected area, the large bodied fishes increase. And that's what you see in the panel labeled B. And so the large body fishes increased in the MPA through time as that MPA recovered. And those large body species were actually found or more typical of relatively cooler water. So they were kind of bringing that CTI down. In addition, an urchin kind of was a range shifting species that has come into this area and of course grazed all the kelp down. And you know this coming from Banfield with all the urchins that are there. There's these huge urchin barrens. Well, now we're getting urchin barrens in Tasmania for the first time. And there's a lot of warm water species. So there's 5 fishes here that are all associated with those barrens because they select barren habitat. They're from relatively warmer water. Because the MPAs have lobsters that are feeding on the urchins, those lobsters were essentially giving a bit of resilience in those MPAs initially. And so that was kind of buffering the MPA from accumulating these range shifting species. And if we think about a community again, and we think in these gray lines as being kind of all species, what we can also then think about with this thermal niche kind of concept is, can we use this in a predictive way for where we're putting our MPAs, not only in a way to predict kind of biodiversity change, can we actually use it to predict where biodiversity might change? And so the blue line is the average that I've kind of eyeballed for this community in terms of what its CTI might be. And then environmental temperature is in the red. So on average, these species in this community live at relatively cooler temperatures than their environmental temperature. So we have this kind of negative community warming buffer. And if we use this kind of buffer, you can actually identify communities that are going to be relatively resilient or kind of relatively persistent under warming scenarios. And in fact, if we use this buffer for our tide pool community in Bamfield, we would have expected that that community wouldn't have shifted given the warming signal that has occurred, because those species are so kind of physiologically robust. And so if we think about this kind of index, what we might expect then is that our CTI is going to match environmental temperature. So if the whole world and communities across the entire globe are distributed randomly, if the environmental temperature is 10 degrees, on average, most of the species within a particular community are going to occur from an environmental regime that's about 10 degrees. But that's actually not what we see. And when we look in our tropical areas, what we find is that those tropical areas on average have a negative kind of warming buffer. There's also some temperate areas that also have a negative kind of warming buffer. And these are the communities with this negative warming buffer where these species are comprised, and you can see this with the CTI, most of the species in that community are actually from areas that are relatively cooler. And so if you're from, and most of your range is an area that's relatively cooler, warming is more likely to have a negative effect. And so a real challenge is that our MPA network is completely exposed to warming, of course, and many other variables. So we're not going to be able to put up borders and kind of protect these areas from climate change signals, unfortunately. So this is kind of a huge issue and something we've been really working on to communicate more broadly to policymakers in particular. And so let's have a little think about this then. So if we have a protected area that's protected from local kind of pressures and it recovers, in this particular example, we have foliose corals kind of coming back into the system. And these foliose corals often have a lower temperature tolerance than some of the mound or Porites corals. And so if we put our MPAs in areas that are likely to undergo kind of extreme heating events, what happens and what has been observed is that we lose these kind of foliose corals from the system in those MPAs where we've allowed them to recover. And we've kind of coined this the protection paradox, because we don't want all of these kind of species or populations that we protect that are also more sensitive to be lost under kind of a disturbance event. And so we can actually predict some of these things using metrics like the thermal niche to predict which species might be more resilient or might kind of recover. And so we can think about integrating this into our marine spatial plans. Okay, so before I take questions, we'll just go through some of the take homes that I think are pretty key, and then I'm excited to chat with you. So basically, some of the underpinning mechanisms are why are we getting such huge variability? And I think some of the clue also comes from biological interactions. So we have range shifts, for instance, in the example that I shared, we have Centrostephanus, which is this urchin that's coming into the system, it's grazing and it's shifting the kind of seascape. And that's in turn shifting habitat preferences and interaction between species. But these biological interactions can also potentially build resilience in our natural systems. And so if we're thinking about biodiversity change and planning for biodiversity change, we can kind of identify where we can build resilience in our natural systems or what resilient components are already there. In addition, baselines have already been altered. So a real challenge is kind of finding sites where we have reference sites, and what that then means is that we can actually track change accurately because we know what kind of impacts or activities are impacting those particular sites. And because baselines have been altered, we often lack the response diversity to potentially respond to changes that are environmental, because we've already lost species or kind of functionality from our natural systems through fishing and other human-related activities. And so I guess in my lab, what we're trying to do is we're trying to build kind of natural insurance into systems using these traits like species kind of thermal indices or physiology, and also functional traits of communities to try and see where we kind of have these levers, these management levers that we can actually implement. Okay, so obviously I'm delighted to take questions now, Luke, and I'm just going to thank a whole bunch of funders and then go back to our beautiful picture of Logie Bay, which is the Marine Institute that I'm now on, which is kind of like the alternate cold side of Banfield. Thank you.
Thank you so much, Amanda. That was amazing. And thank you for finishing. We still have like a good 15 full minutes for questions. And I know that there are several down at the bottom of your screen. If you just bring your mouse to the lower part there should be like a pop-up that has the Q&A section.
Yeah, got it. Sorry, I wasn't clever enough to find that in the during the thing.
I don't know. Zoom has a great way of like hiding the things you don't need until you move the mouse towards. But yeah, this is a wonderful picture you have here too. So thank you.
Okay, so Luke, are you going to read out the questions or should I?
So far, what we've been doing is the speaker is reading them, just so that we don't have to like be the middleman.
Sure. Okay, so there's and can like people chat with me directly, or do I have to read them out?
I'm going to click answer live on all the current 4 ones here, so everyone should be able to see them, and I believe they already could, and people are able to upvote them before we do that. But I don't believe you have to read them out. I think you can just like indicate the name of the person who asked the question so people know which one you're answering. Maybe Great. If you start at the top. Great.
Okay, so Megan asked a question about, is there in the higher intertidal pool, is there any kind of stochasticity or time lag of extinctions? So since the blob event ended in 2016, will you be able to observe the effects of temperature change in later data? Well, that's why we were coming to Banfield this summer. So we were going out to sample these pools again, and that's really kind of a really interesting question. But what's interesting about the Pacific coast is a lot of these sculpins go all the way down to Baja California. So they're found in the intertidal there. So really we're looking at them in the middle of the range. So the temperatures that they're actually undergoing and experiencing in the pools aren't really extreme for the most part. But if we keep this time series going, I have no doubt that the community will ultimately shift if we keep seeing these extreme events. That's my bet anyway. That's a good question.
Nice. And as you answer them, I'll just click done here so that they disappear, so they won't just continue being sort of.
Okay, but did anyone have a follow-up on that, or?
Oh, that's a good question. If anyone does have a follow-up, I'm not sure how the best way to do that is. I think maybe if they just indicate like a new question at the bottom.
Okay.
Then it'll still be a follow-up question that we will just get down to eventually.
Great. Okay, so we have Alexa. Does the evidence for highest abundance at intermediate temperatures in a species range support the abundant center hypothesis? Yes, it does support the abundant center hypothesis, and it's really great when, so Australia is actually an incredible system, because if you take temperature and latitude, so the abundant center hypothesis, is related to the geographic range. And so in Australia, temperature is almost directly related to latitude, because both currents are boundary currents on each side of Australia, and they're running kind of primarily in a north-south direction. So in this case, we got really nice matching. But where you have like the Pacific coast, where you have El Nino years that are kind of moving larval recruits offshore, or kind of mixed temperature dynamics, things get a little, as you can imagine, you don't always have a match in the center of your geographic range if that's not necessarily, if there's not a linear gradient across the environmental variables that are also driving your range, if that makes sense.
That's excellent. I think we may have a follow-up question at the bottom of the Q&A.
That's from Joanne?
Yes.
Yeah. Okay, so Jan said, wouldn't you expect there to be some local adaptation? Yeah, there would be local adaptation, but a lot of these species have it depends on how widely distributed these species are. So John Green is really an expert in these fishes, and he tells me they have really broad kind of recruitment dynamics. And a lot of the variation, for instance, he thinks that we saw in terms of the abundance of the individual species were from kind of oceanographic, kind of supply side of things. So I'm not an expert in these intertidal fishes. I was going to get to learn how to sample them and ID them this summer. But yeah, so we would have some local adaptation. I'm not sure how kind of epigenetic factors play into this. These are all really kind of interesting questions that you can then follow up with. So if you have these kind of long-term data series, you know, they just start generating all sorts of kind of interesting contexts for questions that you can then ask, like this one from Joanne. Susan. Okay. Is the predictive power of temperature the same for species that can move and therefore have the potential to behaviorally thermal regulate? So most of the species that we are working with were fish. So we can really predict what's going to happen. But with our foundation species like our kelps or our corals, what we have found is there's basically death. So we get, you know, when I looked at I didn't show this data, but when I looked in the same system, for instance, across invertebrates, fish, and macroalgae, we saw really very, very similar patterns. But the mechanisms that are underpinning the expansion and extension are going to differ depending upon how mobile those species are and then how broadly distributed they are. And so if you have a very locally adapted kelp, for instance, so Ecological radiata, for instance, is a very locally adapted kelp in Australia. It basically has these spores, and it doesn't have kind of an oceanographic dispersal stage. And this Ecolonia is just getting basically decimated with these heat events. And that, of course, is having sweeping ecosystem changes because it's such an important canopy species. But Susan, I don't know if that answered your question. I think I just went on a little bit of a tangent.
I'm looking at YouTube now and we don't have any questions, but if anyone that's watching on YouTube has any questions, please type them into the chat section and I'll ask them directly of Amanda. Okay, so we've got Colin, who is asking, what mechanisms maintain a community with a higher CTI than optimal for their habitat? Okay, so basically, when we first looked at this, you would expect that, you know, on average, a community would match the environment, but species are basically distributed in a non-random way. And you can think of this as the thermal biogeography. I think that's Rick and I called it kind of affectionately. So because species are non-randomly distributed and we have relatively cold affinity species and relatively warm affinity species, then when communities are kind of assembling and the processes that are causing kind of the assembly of those species are not directly related to temperature. And so of course you can get kind of local adaptation, et cetera, but a lot of these species are really widely distributed. So even in Tasmania, for instance, when I was looking, I didn't show these data, but I looked across maybe about 25 different communities. And those communities all had a really different CTI. And when I looked at the CTI over the 20 years, if that community, for whatever reason, started with a higher CTI, it didn't change as much as those with a relatively cooler CTI. And there's no, there doesn't, like, just because it had a lower or higher CTI in that region doesn't necessarily mean that was kind of a selective response. It could just be because of other reasons for that community kind of assembling. But it also had implications. And I think that's the key thing, is that, you know, we're changing communities in ways that shift the physiology of these communities. And that in turn is going to have implications for how those communities respond to various disturbance events. Okay. I hope that answers your question, Colin. So now we have a question from Emma, and it's about studying MPAs and what do you need to navigate any kind of political challenges with studying MPAs?
Well, every place is very different when we think about MPAs, and there's a very different kind of history. So I'm kind of laughing because I'm having a hard time even figuring out how to answer this question. But I will say, when I published my paper on resilience in MPAs, that I actually had direct emails from fishers for the first time in my life telling me that my work was rubbish. And all I was doing, I was pointing out positives and negatives, and I felt like it was very balanced. So that was kind of an interesting experience. And I think in every place I've been, so when I was in the UK, it was a completely different situation versus Australia, where there's a huge, expansive, no-take marine protected area system. In the UK, there's only a few no-take MPAs. Most of the protected areas in the UK would allow all sorts of activities, from hunting ducks to, traps to fishing. And then coming to Atlantic Canada, there's almost no marine protected areas here. Of course, that's shifting because of various international efforts, and then also the federal government kind of imposing a particular amount of area of our shore to be protected. But historically, there hasn't been marine protected areas. So there's a huge, challenge here with oil and gas, and then also access to fishing and people's cultures and livelihoods. It's not really an easy equation.
This is probably a great time actually to thank you so much to everyone who has had a question, and thank you so much, Amanda, for speaking to us today. I'm Chris Neufeld, one of the instructors of research in marine ecology. Just sent a message to the class, but I believe it only came to us panelists, that once the formal seminar is over, the class will take a 5-minute break and then reconvene on the class Zoom channel. And Chris has sent you a link, Amanda.
Oh, great. Okay.
So I'm just, reading that out loud so everyone can hear that. I think, oh yeah, so then now I think he's been able to send it to all attendees. That's great. We're just getting, like, the chat is blowing up with people thanking you for your great talk.
I can't see anything. I'm just looking at a white screen. So I think it's much more exciting on your end.
Yeah, you've got the Q&A is like oh, there we go. The chat down there has like Heather Alexander and Stacy and
hi everybody. I wish I was there in person.
We do too. We really do too. It's we're really excited to have you out next summer, and or even sooner, as soon as humanly possible.
Yeah.
Again, thank you so much. I'll just take this moment to, I guess I should probably put it in the view of my face here, so I'm not just like, there we go. I'll just take this moment to tell everyone that next week we actually have no formal BMSC research seminar. So we're taking a break from the research seminar just for next week. And that is because we're going to do something special. We're going to have class presentations. So just like normal at BMSC, we'll make them open to the public, and people can join these class presentations where the students will be presenting on their projects. So stay tuned for more information about that and how to join. It will be on Wednesday rather than Thursday. So we're looking at July 15th. Amanda, we hope you can drop in for some presentations to view them at some point. Meanwhile, if anyone has any questions relating to the seminar series or to myself, please email university@bamfieldmsc.com. Let's all thank Amanda again with our thunderous applause emoji. And, Amanda, I'm sure the class is looking forward to interacting with you in a few minutes on the classroom channel.
Great. Okay. Anyway, I'll see the class in 5 minutes. Thank you so much for all your help. It's fun.
Thank you, everyone. Thank you, Amanda. We'll talk to you soon. I'm going to end the meeting for all now.